the end or in the middle. It's attacking an R with an H in that position. Okay? And then this I minus, in this case, the I just refers to like a free radical initiator. What this means is the dot is so this I is not iodine, or the ion of iodide. It is one of these molecules showing that it has a dot on it. Okay, it's not that they just, I don't know why they don't just put the dot, but in this case they don't. So that means that this O, let's say it's O2, all right, so this O2 minus donates this dot, and it becomes O2 again, and now this R has lost the hydrogen, and it has this extra electron on it. That's the initiation. That extra electron is what's going to cause all the damage. And this floats around. We use O2, we use superoxide and peroxide radicals, especially in our peroxisomes, because they are so great at breaking things down. That's what they do. They break down molecules by causing damage to all these different bonds, and then they fall apart, and we can recycle the component parts. In the lipid membrane, that's not so preferable. We don't want to break it down, but if it runs into a free radical, which are created by all of our metabolic processes, we will. So that's step one. Step two. So here's this thing with the extra electron on it. So oxygen, we talked about oxygen being a really good temporary extra electron acceptor, relatively speaking, to our carbon. So oxygen comes along, and this molecule, in order to disrupt this dot, wreaking havoc on the stability of all of the different bonds, incorporates it. And now we have this carboxylic acid, right? Not the H, sorry. So because so if you've got this negative, you've got a double bond here, which is pretty capable of stabilizing that electron, and then you've got another place where it can hop down. So it can go back and forth. It can, if you imagine little dots, right, it can travel back and forth. And this is a little tiny bit of resonance stabilization. It's why carboxylic acid works so well as an acid, because it can donate that proton and still be okay. All right, so that's step two. So now, but we still have a dot. We still have an extra electron. It's relatively happier than it was, but it's not happy. So what's it going to do next? This is the next door neighbor to R. So R first lipid. R prime is next door neighbor lipid. So it's sitting right next to its next door neighbor. This one's totally stable. This one's relatively stable, but now it's a reactive molecule. It's got a double bond OO on the end, which is relatively reactive and wants to react with other things. And it's got that extra electron there, which makes it reactive. Okay, so what is it going to do? So lipid number 1 is going to take the H from lipid number 2. And now lipid number 2 has the problem. But this is not the same as this. R with just H is not very reactive, right? It's not, when you think of R, a long lipid molecule that ends in an H, or that has a ton of double bonds with all of the carbons happy at 4, is not very reactive. Carboxylic acid, which is what you've just turned this into, with or without a proton on it, is much more reactive. So your lipid membrane is not the same as it was when you started. When we looked in 417A at all those lipids, we have the carboxylic acid end, and we have the methyl end. And the methyl end and the carboxylic acid end do different things. We esterify at the carboxylic acid end, which makes those lipids less reactive. We've all of a sudden just given this a reactive end, right? Now, if this happens in the middle, and it happens to attack where there's a cis bond, that's a trans bond, but where there's a cis bond, eventually what will happen is this lipid will break into pieces. Because once you start attacking, instead of saying it's the same number of carbons, once you start attacking those double bonds in the middle, then the whole lipid starts to fall apart. So you end up unsaturated, and then once you're unsaturated, then you attack down here. And if you've attacked strongly enough at a double bond, you can break that double bond off into pieces. It depends on whether you have enough hydrogens capable of saturating that hydrocarbon or whether something else has to happen. But we're going to assume right now we're going to stay down here just because it's easier. Okay, so now, lipid 1 is happier, but next door neighbor has an electron problem. Okay, so what's the next door neighbor going to do? Okay. So, let's see, R dot. So, or, right, because we turned this into ROOH, but ROOH can really easily become ROO dot. Okay. So, these two things find a way to stick together. In other words, here's our ROO dot, which comes from our ROOH. Here's our next door neighbor dot, which is created by the attack initially on the first lipid. So these things would rather be more stable by sticking together. It solves the dot problem. This is like, that shouldn't be dot, that should be stuck together, sorry. Okay, so it solves the dot problem. So when these things stick together, they can go back to being relatively happy. But when your lipid membrane is stuck together, can you pass things through it? No. So all of a sudden, you get these things that are stuck together, which means that the lipid membrane isn't working very well. Okay, so your alternative is the A stands for antioxidant. In this case, it's vitamin E. So this is the alternative, and I'll write this. Now, as we mentioned, we can repair a small amount of the lipid membrane. So if we get a few of these reactions going on, we have the capacity to go through, recognize that they happen, and put them back together. Or splice them out and fix them. Down here, we embed antioxidants in the form of mostly vitamin E in our lipid membrane. We've evolved in such a way that this happens every 15, 20 lipids, phospholipids, because now instead of having these react together and just continuing the chain of sticking together every time you get an antioxidant, every time you get a free radical, if the antioxidant comes in, you repair before the damage even starts. This antioxidant is capable of taking that electron free radical and holding it, and this one goes back to RH. The reason that they put ROOH or ROO dot in here is because you can stop this at any point in the process. It depends on where you come in. So now we know that ROOH is not as happy as RH, and it would be better to stop it at the first step, but that's dependent on where the lipid is relative to the vitamin E. So that's how vitamin E stops lipid peroxidation of the membrane. Does that make more sense than me flying through it last time? Okay. So what does vitamin C do? I'll try to put vitamin C